Today we're going to do chapter 6.2. Let me scan this in first, then I'll write it down. Okay, now this is, let's see, this is the page that's already scanned. Okay, then but I will show it to you anyway. And maybe zoom in a bit on top and then on the bottom. That should be good enough. So next, page 186 and 87. Let's see. Okay, that is, let me make it parallel. Okay, a little closer on top. Okay, and a little closer on the bottom. All right. Okay, and finally, page 188 and 89. That is just a little bit of homework on this page. Let's see, let me hold this right. Okay, that's the whole page. And then a bit closer on top, mostly the homework. Okay, and the bottom. Don't need to worry too much about that. All right, so that should be it. I just noticed that I was wearing the wrong shirt. So, so I had to change that. I think I wore the wrong shirt in the previous video also. Oh well, I was worried that that might happen sometime, but it did happen today. Well, I'll focus and not let that happen again. Okay, so let's move on. I got my right shirt popped on and we should be good to go. So let's look at page 185, double integrals. Now please read the introductory paragraph yourself, okay? And we'll move on to the next part where we have says that we have the function f and g. We have a bunch of properties for that matter. Is about the functions f and g and the double integrals. They are basically identical to the stuff we learned in the past. So, but we'll go over it briefly, but without bothering to prove it, because the proof goes the same way as before, pretty much too. So now the f and g are continuous in the closed region R. Okay, I want to regions are always by now our definition they're always closed, but I want to emphasize the point that they're closed. So f and g are continuous in the closed region R, and k is a constant, and the a is the area of R. Okay, we just assume that is the case, and we also assume that we know that the integral over some area is equal to a. And then R equal to R1 plus R2 in the following property means that these are regions, and then and as defined in the previous section, and then R is made up of R1 and R2, and also that the region R1 and R2 do not overlap. Okay, that's very important, and have no points in common except for the maybe perhaps boundary points. So in that case, then the property 4 will work. And then if R1 as an example, R1 it will be equal to R will be equal to R1 plus R2. If R1 is the half a circle from -1 to 0, and R2 will go from 0 to +1, and R is the entire circle. Okay, and so you just cut the thing in half, and then you're good to go. So anyway, so let's look at the properties. First, the integral of 1 is just the area of the R, okay? And integral, and that's property 1. Property 2, any constants can move out of the double integral. Property 3, if you have two functions added together, then you can split it into two integrals. Property 4, if you have two regions added together in such a way that they don't overlap or anything, then the integral over the entire region can be split into the integral over two parts to two regions. Property 5, if function f is completely less than function g at every point of the function, then the integral of one will be less than or equal to the integral of the other. property 6, the magnitude of the integral of overall integral is less than or equal to the magnitude of the function, the absolute value of the function of the integral. That has to do with Anyway, that carries over from one-dimensional calculus, and the argument works about the same way. And then, of course, the absolute value of the integral is going to be less than equal to the area times the maximum of the function. That again carries over from the previous argument, and we're not going to go into it too much because that is we already did something like this in the previous chapter, I think. Yeah. Anyway, so let's move on, okay, and look at iterated integrals. Now, the iterated integral is integral of the form will go, and this is, of the form where the first integral goes from a to b, and the second integral will go from some kind of from phi of x to psi of x, and as we have drawn before, that is the our x region that we have defined before, so that the x value is the x boundary is the straight line, okay, and then the y value will varies like from phi of x to psi of x, that sort of thing. So we're integrating over that, and this is now if we do that, then let's see, let's go to the next page, page 186. This means that the function f is evaluated defined by the function for each x between a and b, then we calculate this integral. So the way we look at it is we fix x, okay, and then calculate this integral for each x, and then we integrate this new function from a to b. As you might imagine, this definition will work. So the function f is defined as big F is defined as a function of x when you hold x as when you pretend that x is a constant with these functions on as the upper and lower limit, and take the integral with respect to y, and that will give you some kind of a function of f. Then you integrate this function from a to b. All right, so that's how the iterated integral is understood or computed. Now because x, let's see. Now, because we are holding x constant in this part of the integration, let's see where to go, over here. Okay, because x is held constant, then it is during the first part of the integration, okay, when we did this, then it is similar to the process of partial differentiation where we hold something similar. So as an example, let's look at example A, where we have a fairly simple, straightforward, straightforward problem. A is minus half, B is 1, 5x is minus x, psi of x is 1 plus x, and but that's just the boundary. Now we're going to integrate x squared plus y with it, which is still fairly simple, right? Well, it looks simple until you try to do it. Then it gets a little more tedious than I expected. Not bad. So then when you do like it says, then we first we integrate we integrate this thing by holding x constant, integrating with respect to y, and x squared plus y, right? So we get this thing, okay? And then we have to evaluate it from minus x to 1 plus x, then so we get that thing, which and then we have to integrate that thing from minus half to 1. That gets more tedious. Now, I was doing this at 4 in the morning, and I didn't know, I wasn't paying attention, so I actually went ahead and did it the hard way by hand. Did all this stuff and summed up all this algebra and summed everything up, and it actually equals to something that I assume is correct. Yeah, I think it is correct. But anyway, you don't have to do this, okay? I mean, you can just, in the sense that if I were to do it again, I'd type it into some calculator somewhere and not have to do all this by hand. And anyway, so that is example A. So let's look at the next part. We have The next part is we're going to calculate the volume of some solid. All right, and the volume of a solid is, we'll think about it this way. First, we'll start with a boundary C that is on the ground, on the XY plane, okay? And then we put up a perpendicular to the plane, and that is the boundary C is of a simply connected region, so it's a closed curve. Then we're going to stick up vertical lines all along C, and then that is perpendicular to the plane, which creates a cylinder. Now, to remind you what a cylinder is, we mentioned the cylinder before, but to remind you what it is, I have, come on, this, give me a second here. This thing won't get bigger. There it is. All right. Now, a cylinder is, look at the top here, okay? A cylinder is a set of lines parallel to a given line passing through a given curve, okay? So that is a cylinder. Now, so what we're going to do is let's find the volume bounded by this cylinder, okay? The ground, which is the z equal to 0, and the surface on top of the ground, z equals to fxy. So all that will create some kind of a solid, right? We are assuming that f is continuous and f is also positive, okay? And then to keep things simple. Now, if you do that, then here is a picture that I drew of this situation, okay? Let me show you. So here's my curve. The curve, a curve C, right, that is on the ground. We stick up vertical lines all the way around C. So we have a cylinder. This is my cylinder. Remember, the definition of by this definition of a cylinder, the curve doesn't even have to be closed. That is, your sheet of paper can be called a cylinder by this definition, because it is just vertical lines coming along some curve. Right, so so that's my cylinder. Remember, the cylinder is infinite in both directions. Okay, so imagine it extends infinitely both top and bottom. That's a true cylinder. But right now we only care about a small part of it, of course. And then so the next thing is The next thing is then we have this situation. We are considering the solid that's bounded by my orange or colored surface. That's the F. Okay, and then the blue thing is the cylinder, and then the xy plane down here is z equal to 0. So this thing, as you can see, that's created by those three things is the solid that we're talking about. All right. That's the intersection of all those objects. Okay, now first and next, let's talk about the postulates of our volume of solid, just to make things clear. Okay, first, volume is additive. That is, if we have a solid A of volume V, right, and the solid A, however, is composed of two distinct solids, A1 and A2, each of which has volume V1 and V2, then V, the volume of the whole solid, is equals to V1 plus V2. That's the first postulate. The second postulate says if a solid A1, which has volume V1, is part of a solid A2, so the one solid is completely inside the other one, okay, and contained, that is, not just inside but contained, is part of the second solid, then V1, the first one, volume, is going to be less than or equal to V2. All right, so that is the second postulate. So the next thing we're going to do is we're going to make a subdivision of the region R, that is the region bounded by C, and by curves CK, and then push up cylinders on each curve. Okay, and then then you got a bunch of skinny tall things up, right? Then the volume between the cylinder on CK, so each of your little thing is made of the little cylinder, right? If you want to call it that, of each individual curve, and the surface is ZFXY. That didn't change. The surface is still up there, and the plane Z equal to 0. And then we'll call that volume delta VK. So each little stick long stick there will be called VK, as I have drawn here. Now I have divided this. See, my my C got actually divided into 4 pieces. Okay, each one of these things it can be considered a closed curve, even though it has a sharp corner. That's fine. The curve doesn't have to be smooth. So each one of these, consider, for example, the one that I call SK. So that one is a little closed thing. So, and then I erected, like it says, erected cylinders all the way around. So as you see my division planes there, the gray planes. So then my cylinder got broken up into 4 of them. Okay. By now, so 4 chunks of skinny cylinders. Not skinny, 4 volumes. Okay, my volume got divided into 4 volumes. Each has its own cylinder. And the cylinders, of course, they have common cylinders. The cylinders are common where the boundary is the same. Okay, and the joining boundaries. And to show this more clearly, I have drawn just one of them right here. And this is only the one in the corner where it says SK. Okay, and as see up here in this picture where it says SK, that is this one right here. So this one just shows you one of them where the boundary, where the cylinder goes around that triangular shaped sort of thing, and then F stays on top, and and then so this new little cylinder consists of the old cylinder, which is blue, and then the vertical walls around this side and this side, which I didn't draw so that you can see the things clearly. Okay, but you can imagine, I draw a purple line so you can imagine it. So these walls are transparent, let's just say. Okay, but you can see at the corner edge, which is the purple line. All right, so that's what that looks like. You can imagine. So there's 4 of them in my case, and of course we're going to divide this by far more than 4 pieces. But to start out, let's imagine just 4. Okay, but as you imagine more and more, this thing being split up into more and more things, they all look similar. Just get smaller and smaller, but that is skinnier and skinnier, but the height stays the same. So you get all these sticks coming out, and each one has its own little cylinder wall, and and they all becomes part of the volume of whatever it is that we're making. All right, so that is that. Let's continue reading the bottom of page 186, where it says, if we'll pick 2 points, okay, xk prime, yk prime of f, and then xk double prime and yk double prime of f. What about these 2 points? These two happen to be the points where the function f are minimum and maximum in that little stick. Okay, only in the subregion bounded by ck. So we're able to find the maximum minimum. We assume that is the case, being that f is continuous on a closed curve, closed region, and all that. So we can find these maximum minimum, and then from the volume of the cylinder, then we can conclude that the maximum times the area. First the minimum times the area is less than the volume of that stick, okay, because we're doing the minimum, and which is less than the maximum times the area, right? And yes, let me see. And the reason is because the minimum is going to be completely contained in the volume, right? Because we said is, so by postulate B, that is true. Okay, so next, on the next page, let's go to page 187, and then where we call the delta sk is the little area on the bottom. So the area times the height will be an estimation of the volume of the stick that we have going straight up, and then right. Let's see. Okay. And of course, the volume of the actual thing will be the maximum, between the maximum and the minimum calculation of f. And then next, we see that so then when we add things up, by postulate A, volumes can be added properly, okay? So then if we were to add them all off, in our case, in my example, only 4, but however many we have it sliced up, the principle is the same. If we add it all up, in each minimum, right, then the minimum of each little sk, when we add it all up, it's going to be less than equal to the actual volume of the solid, which is less than equal to the maximums. Now notice these minimums are only calculated on your little area, okay, of the stick. But that still works, right? So when you add it all up, it's going to be less than the volume, which is less than the maximum, times the area of the little sticks. All right, so now this is looking very familiar, right? And so being that the sum is the same sum as we learned in Theorem 1 in the previous section, then we can argue that if this sum, if we not push the norm of the subdivision, that is the maximum diameter of the subdivision, and push it to 0, which means n has to go to infinity, then we see by Theorem 1 in the previous section, well, basically Theorem 1 just said that then in that case your integral exists if the f is continuous. Okay, that is okay. So that is that. I want to show you these graphs again. You don't have to graph this. Okay, I just did it for fun because I like playing with Desmos, and this gives me a good excuse to come up with something and draw all the stuff. And look at how Desmos can let you do all these things. Okay, and it makes an excellent demonstration, and I don't have to draw anything. Let's see. Yeah, so these are just divided by 4, and then the last one, then you can see just one of them. And in case now you don't have to do this yourself. Okay, I don't see that will give you any particular benefit except for the fun of doing it. So if you enjoy this kind of thing and want to do it yourself, then you can. And I want to just show you quickly the formulas I use to do this. I think they are. Yep. They are all here. Okay, I just show it to you real quick for anybody who want to draw it too and wonder how and maybe run into some problems and wonder how I did it. So here are all the formulas I believe that's necessary to draw this, and also experiment yourself. Just type in this, that, and see what comes of it, that sort of thing. All right, so that is that. Next, there's example B, but that's really straightforward. So please read example B yourself on page 187. And then we have come to the, let's see, what is this? Come to the end of this section, and we need to talk about homework. So for homework, please do, this is page 187. Please do problems 4, 5, 7, and 13. The homework isn't really much worth doing, but I did some of it, just so, which I'm going to show you right now because they're not really worth mentioning either. So I will show it to you in case you have any questions about it. Okay, and that is a bunch of integration from Calculus 1. That's about all we're doing. Yes, and for problem 7, I want to show you that there's actually I used the calculator to do it because I wasn't about to do it myself. I'll show that to you in a second. And then problem 13 is slightly more worth doing. Is to prove the MVT, the mean value theorem. But it's not really much worth mentioning because if you just follow page 162, I just basically copied word for word from the same. The proof goes exactly the same way, okay, and with some notation changes, that's all. So that's all I did. I just copied it, and it worked out very, very nicely. So that's problem 13. Now, going back to problem 7, and I want to show you how I did the integration on the calculator. All right, this is problem 7. Now, as you can see, give me a second here. Now, problem 7, we have, let's see, what is this not bright enough? Things don't seem very bright, okay? Let me see. Let me check something. Anyway, so let's look at problem 7 real quick. I just want to show you how I did the integration on the calculator, a Wolfram integral calculator, where you click this tab, okay, and then click the double integral tab, then you can type in all kinds of symbols. Look how smart this thing is. And then it's able to calculate exactly what this integral is for problem 7, so that I didn't have to do it by hand. I mean, who wants to do this by hand anyway? So then, so that's it. I wasn't able to do the others though, because when this thing has a square root sign inside, then it croaked, and I couldn't get problem 8 to come out, and it's not worth doing anyway. So that's why you're not assigned to do that. And that's the end of this section.